So we have again another beautiful topic, and which we call as temperature scales. So when we consider temperature scales, we consider these temperature scales in different versions. How this temperature can be measured in different areas. One of those will be in terms of Kelvin, which you can refer to as thermodynamic Kelvin. Thermodynamic Kelvin. So the other point again, which we also call as the Celsius scale. We also have again the other one, which we call as the Fahrenheit scale. And these are the three areas which we are going to consider. Because temperature can either be measured in terms of Kelvin, or in terms of Celsius, or in terms of the Fahrenheit. So in this case, the broad scope of this topic is how we can be able to find the relationship that connects between Kelvin to Celsius, or Kelvin to Fahrenheit, or Celsius to Fahrenheit. You see. So let's consider the Celsius scale. And we consider again the Kelvin scale. So the next point again, we also consider the Fahrenheit scale. So we consider the Fahrenheit scale. So we consider all these. So this. So we consider these three scales because the focus here is really how we can consider the Celsius scale, the Kelvin scale, and the Fahrenheit scale. So the relationship here we're going to consider, let's say they consider the Celsius scale is in three versions. So this brought us to another three key terms, which we call as the lower fixed point, the upper fixed point. This is the upper fixed point. This is the lower fixed point. And this is the fundamental interval. These are some of the terms you might be asked to calculate. What do we mean by the lower fixed point? The lower fixed point is the temperature which corresponds at the ice point. You know, the ice point is measured at 0 degrees Celsius. While simply the upper fixed point is the temperature which corresponds at the 100 degrees Celsius. So in simple point, lower fixed point is the temperature which corresponds at the ice point. And the ice point is calibrated at 0 degrees Celsius. And simply the upper fixed point is the temperature of the steam, and here is the ice point. So the temperature which corresponds at the steam point is at 100 degrees Celsius, and the temperature which corresponds at the ice point at 0 degrees Celsius. So that temperature we call the lower fixed point, and this again we call it at the upper fixed point, which corresponds to the 100 degrees Celsius for the steam point. So having captured those 3 points, always for the Celsius scale, always the lower fixed point is 0 degrees Celsius, while the top or the upper fixed point is 100 degrees Celsius. Since we are looking for the Celsius, let's use the C. So we'll move again to the Kelvin scale. The Kelvin scale again, we have to know those fundamental values. For the Kelvin scale, the top value is 373, always Kelvin, and the lower value is 273 Kelvin. Since we are looking for the Kelvin scale, we write scale. Furthermore, we go to the Fahrenheit scale. The same way, let's say the Fahrenheit here is at 32 degrees Fahrenheit, and we represent here F because we are looking for that value. And here, 32 plus 180 will give us 2 212 degree Fahrenheit. The same way here, 273 plus 100 will give us 373. This is how we capture this value. So the purpose of this lesson is how we can have the relationship between these temperature scales, which in terms of Celsius, Kelvin, and the Fahrenheit. So if we compare the difference between Celsius and Kelvin, we interpolate, we say by interpolation. That means we compare these two scales. When we interpolate, we have to be consistent. If we start with C minus 0, and we say 100 minus 0, you have to do the same thing for the other side. Since we say C minus 0, this other side must be K minus this, which can be written as K minus 273 divided by, since here we say 100 minus 0, 100 minus 0, here you're going to be 373 minus 273, which is 373 minus 273. C minus 0 is C, 100 minus 0 is 100, K minus this will remain how it is, and 373 minus 270 is 100. So carefully, 100 cancels 100, therefore C equals to K minus 273. So this is the relationship that connects between the Celsius scale to the temperature, to the Kelvin scale. So suppose you are required to convert Celsius to Kelvin. If you are given Celsius, let's say 30 degrees Celsius, how can you convert it to Kelvin? Just put 30 here, you equate it to K minus 273. Therefore, you transpose, so 30 plus 273 equals to K. So when you add, that will give you your Kelvin. So this is a relationship that simply connects between the Celsius scale and the Kelvin scale. So if we move again, in another version, how can we compare the Celsius scale to the Fahrenheit scale? If we consider that again, we do the same by interpolation. If we interpolate, let's say C minus 0, you can do it to your choice. You can either say 100 minus C. Anyhow you do it, you are going to arrive the same. But consider C minus 0 and 100 minus 0, which is more easier, and equals to, since you say C minus 0, here you go to the F minus this, which is F minus 32, divided by, since here we say 100 minus 0, here you go to the 212 minus 32. So C minus 0 is C, all over 100 minus 0 is 100, equals to F minus 32, this minus this is 180. 0 cancels 0, so we have C all over 10, equals to F minus 32 all over 18. 2 into A is 5, 2 into 18 is 9. So C all over 5 equals to F minus 32 all over 9. So this is the relationship that connects the Celsius scale and the Fahrenheit scale. So this is it. So consider the last one. Since we have captured the Celsius and the Kelvin, and the Celsius and the Fahrenheit, now the last one to capture the Kelvin to that of the Fahrenheit. We do the same thing by interpolating. If we interpolate again, it's going to be K minus 273, that this minus this, divided by 373 minus this, the upper value minus the lower value, equated to F minus 32, and divided by 212 minus 32. So we have K minus 273, this minus this is 100, F minus 32 maintains, 212 minus 30 is 180. So having this, 0 cancels 0, 3 into here is 5, 3 into here is 9. So we have K minus 273 all over 5 equals to F minus 32 all over 9. So this is just the basic relationship that connects these three scales. But you can capture, you can C equals to K minus 273. If you substitute C here, it's going to be as this, because it's going to be C minus C upon F, and the right hand side maintains. You see, this is just the difference between these temperature scales, and it also leads you how you can compare or how you can interpolate between these values. So we have this example which we are going to solve together. which says the table below shows readings of the resistance and pressure of a platinum resistance thermometer and a constant volume gas thermometer respectively when immersed in the same liquid bed. So we are given the table. This is the ice points. The ice points for the resistance thermometer is 5.67. So after having this table, use the data to determine the temperature of the bed, the temperature of the bed on the resistance thermometer and the B part gas thermometer. And the last point, when the resistance and the pressure are 7.43 ohms and 9.33 times 10 to the power 4 Pascal respectively. So that's it. So by what percentage is the temperature measured on the platinum resistance thermometer in error? You see, so this is just the basic point. From what we have done under the temperature scales, we can have our temperature scales. Let's say we have the first one simplified at this form. If we consider the resistance is in ohms. The highest point of the resistance is this, which is 5.67, and the steam point of the resistance is this. So let's have here the resistance, which is R. Let's represent as R. What's the highest point for the resistance? Is 5.67. While the steam point for the resistance is 7.75. You know, the highest point is here is measured in 273 Kelvin, and the steam point is measured 373 Kelvin. This is the first diagram we are going to consider. So we consider the other diagram again for the pressure. The pressure will be the same thing. When you come to the pressure, while the highest point for the pressure is this, which is 7.13 times 10 to the power 4. And what is the steam point of the pressure? Which is 9.74 times 10 to the power 4. And the highest point for the pressure is the same, 273 Kelvin. And the steam point for the pressure is the same, 373 Kelvin. And the assist pressure, let's use P. So these are the values. And the first part, we are going to find the resistance thermometer, which is R. This is the thermometer we are going to find. This is our scale of reference. And the B part, the gas thermometer. You know, the gas is measured in pressure. So these are the two things we are required to find, which is very, very simple. So if we interpolate, say by interpolation, let's say we say R minus this value, R minus 273, divided by this minus this, which is 373 minus 273, equals to, right? So since we have this, but there is something we need here again. Let's go through the question. When the resistance and pressure are this, so the resistance at this point is 7.43. So the resistance is given as 7.43, and the pressure is given as 9.33 times 10 to the power 4. Good. Now, since we say R minus this, divided by this minus this, the other side again is going to be this minus this, which is 7.43 minus 5.67, divided by 7.75 minus 5.67. So if we maintain this, R minus 273, 373 minus 273 is 100, equals to 7.43 minus 5.67. We have something like 1.76 divided by 7.75 minus 5.67. We have something like 2.08. We cross multiply. R minus 273 equals to 100 times 1.76 divided by 2.08. So R minus 273 equals to, we say 1.76 divided by 2.08. We have this times 100. We have something like 84.61538462. If we transpose, so 84.61538462 plus 273. So this resistance thermometer will be plus 273. So we have something like 357.615. Since the resistance is Kelvin, so we measure it in Kelvin. 615 Kelvin. That's the first value. So if we consider getting the next value, let's interpolate again the next one for the resistance, for the gas, for the pressure, for the gas, for the pressure thermometer. If we interpolate this again the same way, we say P minus 273 divided by, we say 373 minus 273 equated to, here again the same thing. So we say this minus, is going to be this value minus this value, which is 9.33 times 10 to the power 4 minus 7.13 times 10 to the power 4 divided by this minus this again, which is 9.74 times 10 to the power 4 minus 7.13 times 10 to the power 4. So we maintain this divided by 100 because this minus this is 100. Here, you can see 10 to the power 4 is common. So it's going to be 9.33 minus 7.13. Here again, 10 to the power 4 is common. So 9.74 minus 7.13. So if we maintain this, 273 divided by 100, 10 to the power 4 will cancel. Definitely these two values will cancel. So if we subtract 9.33 minus 7.13, we have something like 2.2, and 9.74 minus 7.13, we have something like 2.61. So if we cross multiply, it's going to be 100 times 2.2 divided by 2.61. P minus 273 is going to be 2.2 divided by 2.61. What do we have? Times 100. So we end up having 84.29118774. We transpose the 273 because this is minus. When transposed, it's going to be plus 84.29118774 plus 273. The gas pressure plus 273, we have something like 357.291187 in Pascal, because pressure is measured in Pascal. So the gas pressure or the gas thermometer is this. Approximately, you can say 357 points to 3 decimal places, 291 Pascal. So this is for Roman A, and this is for the second part of the question, the B part. So the C part now says, by what percentage is the temperature measured on the platinum? The platinum resistance is for this. So our focus is this here. You see, measured on the thermometer in error. So we have to first find the error. What is the error? We see error equals to the real value minus, going to be the corrected value minus the real value. So we find the error of the two, we consider the pressure at the gas thermometer and this resistance thermometer. You can see 357, so you can see the resistance thermometer is greater than this. So you go to the error, now you're going to be the resistance at the thermometer minus the gas thermometer. So we subtract 357.615 minus 357.291. So the error here, in this case, 357.615 minus 357.291. We have 0.324. This is the error. So we are required now to find the percentage error. Percentage error is going to be the error all over the actual, you see, times 100. What is the error? This is the error, which is 0.324 divided by the actual now. Which actual are we going to consider? This is where the question lies. Because the actual, we have two values in terms of the gas and in terms of the resistance. But the question says, by what percentage is the temperature measured on the platinum? So our focus is on what? On the platinum resistance thermometer. And the platinum resistance thermometer is this. So this is the value that we need to consider. So it's going to be 357.291 times 1 meter. So the end of the day, what do we have? We have something like, if we divide 0.324 divided by 357.291 times 100. So we have 0 point, so percentage error equals to 0.090682%. So approximately 0.091%. So this is the percentage error. Thank you all. I hope you have learned something new. Stay blessed. Continue to subscribe on our channel. Thank you.